Hope am I audible to you? You just put a message on box, chat box. Okay. Yeah, today we are going to discuss this cantilever. If you have gone through the syllabus, the half part of the mostly this syllabus contains yours means half of the portion we covered before the Diwali, three-fourth probably that portion we covered before Diwali vacation. But the next portion is containing that bending of beams, cantilever, and sorry, there was some disconnection from my side. I don't know, but yeah, I'll just share the screen once again. Hope you are seeing the screen. Okay, so today we are going to do this discussion on the cantilever. So, so before going to this, I'll just start the recording. So, okay. So, recording is already started. Okay. Yeah. So yeah, so basically the cantilever you can define like if you fix you have a beam, okay, and suppose you want to fix one end of the beam and just another end you keep certain weight at another end, okay, so it will be a when you have a just put a weight, so there will be a bending of that particular beam, okay, because one end you held constant with the rigid support, while the other one you just pulled it with the certain weight. So this kind of beam position we called it as a cantilever. So cantilever is just like a horizontal beam, okay, which got bended because of the what we are putting some weight at the one end and another end we just keep fixed, okay, and that means the cantilever. Okay, so that's the definition of cantilever. So how is this cantilever is going to have give you I mean to say this if this is the kind of a beam and it is in like a cantilever, and we applied a load at its free end or its middle portion or the because of the weight of its own, okay, how is it that bending of beam that we discussed yesterday, that going to be a change. So that what we are going to discuss today about this cantilever. So cantilever is a, already I mentioned, it's a beam fixed horizontally at one end and loaded at the other end. So here I'm talking about a particular case that's I mean to say a particular thing like suppose you have a three cases. The first case, uh, does that cantilever, okay, when it got bended, when you put a certain weight over here, that because of its own weight may be a possible, or when we put certain weight across here. So so that's what we are going to discuss. Okay, there are the three different cases about this particular cantilevers, what we say, that particular cantilever got bended, okay, when we have to consider the only weight that we have get attached to one of its end, like this particular case W. In that case we are not considering its own weight of the this particular cantilever, okay, or you say beam, okay, getting. So this beam weight we are not considering, okay, and that's what the when the weight of the beam is ineffective, that ineffective means that we are not considering the weight of the beam over here, whatever be the weight we applied at one of its end, that the weight is responsible for the what, that particular bending of this beam, okay. So this is the cantilever loaded at the free end, and we here consider to find, okay, this bending moment when the what, the W, that's the weight which is what we are going to be put at one of its end. So yesterday we discussed about this particular beam, bending of beam. Also we discuss about the concept of the neutral axis, okay. So here remember, here this beam is got bended because we have put certain weight, it's one of its end, okay. So suppose we consider this is the AB, okay, originally A is a one end of this particular beam, B is another end of this beam, okay, and which has a length capital L over there, that's the original length of this cantilever. So neutral axis, that means what, yesterday we defined that neutral axis, that axis which got doesn't got any deflection, that doesn't got any elongation or compression, that get balanced at the particular axis, that's what we called as a neutral axis. So this neutral axis has its original length, and that we called as the length L, that we have, okay, and we have apply over here the load that we have, say weight W at the another end, that another end we called as a W, another end we called as a B, and that weight we apply is the what, W, capital W. And now because of you apply that W, the weight, the end B is deflected, or you say depressed. Depressed is a word generally we use mechanically, okay, when you put a certain force or a weight, okay, that's a tension which is acting on a certain direction because of the gravity over here, and that's the what got deflection to that particular beam, okay, and that's what we call the terminology over here, the deflection. So deflected from the original position or depressed from the original position, like that. So you have the originally it has to be AB, but later when it was deflected or depressed, it has a new position that we called as a B prime over here. So B prime is the position of the new neutral axis. So AB prime takes the what, the new position, that is AB prime over here, okay. So AB prime being assumed that the weight of the beam itself produces when the AB it has no weight, okay, and when you have a certain apply certain weight, it has some new position, that is what AB prime over here. Now we need to consider similar concept. Yesterday we talk about this cross section of this particular area of this particular beam. So here again the same concept to be taken. That is what we consider. Suppose the section P of this beam over here. So this point P represent the section of this particular beam, and which we kept at a certain distance, that is what distance x from the its original position. Okay, so original position means the fixed support, that is at the end that is at end A. So we need to consider that this particular section P, which is located at the distance x from the fixed end A, the moment of the external couple at this section. So how you calculate? Yesterday we know the formula, that particular bending moment acting on this particular length. So the total length is what we say, total length is L, and this particular section which got bended, so remaining portion got what this particular bending moment. Okay, so whole the portion is bended, but I'll say suppose we consider the point P over here. So how much torque or couple acting at this section, that what the section is what the PB prime over here. So B prime is a new what we say deflection, and from the point P we consider that's what the PB prime will be the length arm, okay, on which this couple is acting. So this couple is nothing but a torque, okay, that the tension, that is the force that we say whatever is the weight, that is nothing but a mass into gravity, okay, that W with the what this PB prime over here. So what is the magnitude of this W is the W, and the magnitude of this PB prime is comparatively we say it is has the original length L, so small l, so not a capital L, small l over here. Here consider, sorry, capital L. It should be a capital L. Here length should be a capital L. That's the original length. So original length is minus x will be the what the PB prime. So PB prime has a magnitude has how much W into L minus x. Hope up to this particular thing you understood the things. Okay. So now I'll just discuss. I'll move on. Since the beam is in equilibrium and this must be equal to yig by r. So yesterday we talked about this bending of beam is equivalent to the Young's modulus into the moment of that the geometrical moment of inertia divided by radius of curvature, and we define that geometrical moment of inertia in terms of its area and the radius of gyration. So that equation yesterday we have, okay, that's yig by r equal to yak square by r, where r is the radius of the curvature of that neutral axis when we take that position P over there. So therefore here remember this WL minus x, can I write yig divided by r? Yes, we can write, and we can write this equation 2 now. So equation 2 that you are getting, this is the what W into L minus x, which is nothing but a moment, bending moment magnitude, which we write equivalent to yig divided by r. Okay, here. Now since of the load increases as we proceed towards the fixed end, now you have just like you apply the weight, okay, and this loading you are going to be increases as we proceed towards the what the fixed end, that is what capital A. So the radius of the curvature is different at the different points and decreases as we approaches the what the point A. So as you see over the figure, you can understand from this point, okay, if we are approaching towards this point, fixed point A, your radius of curvature goes on decreasing. Okay, the radius of curvature is more and more when we are moving towards the point B prime over here. So remember, originally what will be the radius of curvature? It will be a r theta. Okay, but now we need to determine there we need to determine what will be the small increment. Suppose you consider again here small point position on this PB prime, and that PB prime we consider some position Q over here. You understood here? This is the point Q over there, and we Q and P point, that as nothing but a arc, okay, they makes an angle, subtended angle at the what the center of this curvature, and that angle is d theta over there. Okay, so look at what I'm going to explain to you. So this PQ, or you say for a point Q, at a small distance dx, a small distance dx, I'm talking about this Q is situated at a small distance dx from the P, okay, and which is obtaining an angle d theta over there. So can we write down the PQ's magnitude? Yes, that arc is nothing but what, the radius into the angle which is it's subtending. So therefore PQ is equal to r d theta, you can write over the here. And therefore this PQ, we are talking about the small displace, I mean to say Q, which is a position from P of magnitude dx. So small dx will be a what, this PQ magnitude. So therefore dx is equal to r d theta, and the angle subtended there, we say angle POQ, okay, is a d theta over there. So d theta is the angle subtended, dx is the what, the displacement. So r you express as a dx by d theta over here. Okay, that is the radius of curvature. So can you people just substitute this r with this dx by d theta in our earlier equation number 1. Okay, in earlier equation 1 we need to substitute this r, which with have value of dx by d theta, and that we just put it over there and solve further. So wl minus x, that becomes a y a k square d theta by dx, that mathematics, and by d theta you just express as wl minus x dx divided by y into to the neutral axis at P point and Q point. Means what? Suppose you are drawing a tangent point P and this particular point Q. Okay, so P, which is the, when we draw the tangent which cuts at the point C, and we have a Q point over there, and then you have a draw a tangent that cuts at the what we say actual, not at B, but I say suppose you draw a perpendicular, okay, and extended that particular B prime. So that's a perpendicular which is at end B that cuts at the position C and D. So what I'm talking to over here, this C and D are the what, the vertical positions, or the they are the what giving me the magnitude, okay, or the what we say that the depression produced, okay, along the y axis. Okay, suppose you have this is the what you apply weight at one end, and what the deflection, so that deflection you need to determine. So originally which is at the horizontally, and now it is a deflected, so how much that deflection happens, okay, how much that depression is produced, that we need to calculate it over here. So small depression, small value of that depression we need to calculate it by this particular equation. So how that, so here the tangents to be drawn to this vertical line, and that cuts at C and D, and they subtended the same angle d theta at P and Q, and being perpendicular to this tangent. So therefore the depression of the Q below P is equal to CD, and this is what the magnitude we considered as a dy. So just go to that diagram, you can see that. Now I'll just say that these are the tangent, because you have a depression, okay, and new deflections, you have some points PQ, and that particular what we say corresponding changes to be observed. Okay, on the what the perpendicular axis, you say the new position, that particular deflection has a magnitude of what, CD, and that magnitude depression produces, we consider over here dy. Okay, therefore what is that dy? Dy should be how much the length over there that depression produce, okay, and how much that angle it is subtended. So that's d theta is the L minus x into d theta will be the what the depression produce. Why this? Why we are writing this equation? Because the angle that subtended, that is equal to the d theta. Okay, and the radii is what, P and Q already. But these are the what the tangents we drawn. Okay, basically they are these positions P and Q are perpendicular to it. Therefore, dy we can write as L minus x into d theta. Hope this mathematic part you understand. So we, by the geometry, okay, you can write this dy is equal to L minus x into d theta, and therefore you just substitute the value of d theta from the equation number 2, and you can solve further to get the value of dy over here. So remember, this dy is nothing but what the deflection produced when you have a small cross specimen cross section PQ you consider, but what the corresponding changes happens in the vertical line, okay, what the corresponding depression, that you need to determine that particular magnitude, okay, and that magnitude you consider as how much small change over there, and that magnitude you consider calculate over here by the what, CD, okay, and that's what dy. If you want to compute whole magnitude, how much the whole deflection to be a produce, you want to integrate this expression, okay, this depression expression for y, and you can say this is the total depression y, which is a produce when the bb prime, okay, loaded at the end b, and below the fixed end we say fixed end a is obtained by just integrating the what, the expression for the dy, and we need to take these limits of those integration from x is equal to 0 to x is equal to L over here. So don't confuse with the printing mistake. So this is the capital L is the limit of integration over here, since we are taking capital L as the length of this particular beam. So this is the what, the whole I mean to say depression that we need to consider, okay, along the what, the BB prime. So hope you understand this derivation and why here it is calculated as an integration of 0 to L, and you solve further the steps that you are getting for this dy, and you just integrate to get the value of what, this particular y. So here I am, y is talking about the depression, okay, produce at its free end, that is what the b end you say, and this particular expression which comes out to be when we are solving, putting integration and solve the limits, I mean to say putting the limits and solve upper and lower limits, you can solve I mean to say you can get it the value in terms of this capital L, so which comes out to be WL cube divided by thrice y ig over here. So this ak square again substituted with the ig by considering the geometrical cross section over there. Okay, so the free end of the cantilever you say depressed by how much amount, this particular amount W L cube thrice y divided by thrice y times ig when you are solving further. So so this is the what we can say that you understand the depression. There are the two new things we are going to discuss today. One is a cantilever. That cantilever, when you fix, that means a horizontal beam, it becomes a cantilever when you just put a certain weight one of its end. Okay, and because of you put a certain weight one of its end, it got depressed, that it got bended, and that bending moment we have to compute it in terms of how much it got depressed from the original position. Okay, and that's the depression is what we say perpendicular to the what, the original original length of AB, and that's what this depression is calculated in terms of y. So don't call it as here the bending of moment. We yesterday talked about how much it got bent, okay, and that bending moment is what yesterday we talked about, how much couple act on its one end, how much magnitude on that particular couple is acting. That gives you the bending moment. That WL minus X is the magnitude of the bending moment. But we solve further and get to calculate how much depression or the amount of depression deflection is get produced by this cantilever. Okay, so the free end of the cantilever is deflected by this amount. Okay, and that amount we calculated as a y is equals to WL cube divided by thrice capital Y. So don't confuse with the y. Small y is talking about the diffraction and capital Y is talking about the Young's modulus of the material of this particular beam. Okay, so we are running out of the symbols every time, so don't confuse with the symbols. So symbols are used according to our convenience. So small y, here the depression produced and which is related to capital Y and is inversely proportional to capital Y, that is the Young's modulus of the material of this cantilever, say beam. So look at this cantilever, we called it as a cantilever because that beam is going to be a deflect. Okay, then you say that it's a cantilever. So this is the like a mechanical thing. When you first case we consider this deflection, depression is not produced because of its own weight. But suppose you consider another case number 2 over here, and in this case we consider when the weight of the beam is effective, I mean to say its own weight is responsible for the what that particular deflection. Okay, then we have to consider the different what we say, I mean to say that weight is also added here in the what our derivation. So remember we need to take modify when we are solving this case number 2. So case number 2, here we need to consider the weight of the beam. Okay, and that weight of the beam is added into the what the weight that we put it one of its free end, remember. So here in this case particularly, when the what we are addition this particular weight W at the what its free end B, okay, the weight of the portion that L minus X of the beam is also acting at the midpoint of the center of gravity of this portion. So suppose you have a beam and it got bended because you have put a weight, okay, and that bended portion, okay, arch portion is also having its own weight, and that its center of gravity, okay, that we need to put it over there. Okay, so we need to consider this small w be its weight per unit length of the beam. Okay, and this is what we consider a point P over there, I mean to say. Suppose so again you want to go to this geometry, so what's your point? Your point is over here is a P. Okay, get it, and that is get bend. So what your portion, that L minus X portion is going to be a bend. So W, that small w into L minus X, which is actually that whole length, what we say has to be added. Okay, so WL minus X is acting at a distance, how much average of this particular section, you say PQ. So we have considered this section is at a distance X from the fixed end, so L minus X, so we take a average of it, and that average value of the distance, okay, this particular weight is going to be a put. So like a moment, bending moment which is acting on its average length. Okay, so therefore when you are writing the total bending moment of the beam, so total weight of the this particular beam is capital W, how much length it is acting, so that L minus X, WL minus X gives me a one of its bending moment to the total what we say length. Okay, or you say this is the bend portion from where the position we have taken, that position P. Now the next bending is because of its what we say, its it's because of its own weight, and also because of the what, on particular length over there. So WL minus X multiply with the how much average of the length is which is acting, that also get I mean to say product with this quantity. So hope you understand this mathematics part. So this part been considered on special case, and special case means this is another case we are solving here, where we are considering some approximation like that. Okay, this portion has its own weight, okay, and that acting over the average length, and that's what you can write the bending moment of this portion. So you can see that this terms is added over there because of its own weight, okay, and that's the small w by 2 L minus x whole square. This particular term is adding over here because of the weight of the beam is effective over here. Getting, so your new what we say bending moment will be this one, okay, not, it is just not be the our original one w original, you say case 1 case we called it as this wl minus x, w times l minus x is the bending moment, but here this bending moment becomes added with this small w by 2 L minus x whole square, okay. So you will have this new equation, and that you new equations you write this particular bending moment is equal to y square by r, or y into ig by r, which is the same thing, and this d theta by dx you already calculated in our earlier expression, so that d theta by dx will be remain as it is there, okay, and you just writing here the d theta in terms of new bending moment. So your expression for d theta this new what we say bending moment I mean to say get modified over here, okay. And so new expression, if you want to solve for further for producing this y uh, dy for small portion, okay, you have to use the same terms, okay, and you have to solve further. So you have to just find the total depression produced, you want to do integrate within the limit 0 to capital L and solve this equation further. So you will get a small y is a depression produced because of the what, this beam got deflected because you put a certain weight, also you have its own weight, okay, and that weight is added over there. So that quantity we are here we considering again this small w is right in terms of capital W1. This is for just for consideration that the whole weight of the beam here we consider, and you can I mean to say you can just generalize this formula in terms of the formula, okay. So here WL we are writing as a W1, and small w, okay, small w into capital L as a W1 for just for the understanding things, okay, and you just express in terms of this depression produce, okay, in terms of the this capital W and W1, but which are the both are the different quantities, okay. So the beam now behaves, it is loaded at one end with a weight as the same weight, plus the weight is the thrice by 8 of the weight of the beam over there, okay. So so total weight we consider over here, this is small w, so you have to just be clearly understood that what is the small w over here it is considered, and capital W. Capital W is the what weight we are putting, and small w is the what the basically the center of gravity of that portion, okay, that bended portion that we consider over here, which acts over the average length, okay, and that's what that small w comes over here. So that small w into capital L, that suppose we write as a w1, and then we can talk about that, okay, when the beam has its own weight is added, then we say that then the b then that portion is we say that equivalence to the thrice by 8 of the weight of the beam, you say. So this is the equation we are getting in another case number 2. You have all three cases been mentioned in your syllabus. That is what I want to discuss first two cases, and another case is case number 3. where we say that this cantilever is loaded uniformly. Okay, what does it mean? It means that when you put a weight, okay, on the cantilever, so it's just like one fixed end, and you put the weight on equally on its bending portion. That's what the uniform loading. It is not just you are putting weight on the what one of its end. So it's like you have just consider that weight is low, that whole cantilever is held at a fixed position and free at another position, which has a loading uniformly all over its length. So that is the uniform loading we called. Okay, and so therefore let me consider the uniform loading on the cantilever be small w per unit length. Okay, and the weight of the portion that we consider becomes a small w into L minus x, that produces a bending moment about the section PQ. So look at the geometry of the figure we are considering here again. So you have to be a very clear in your mind this particular figure. That's what when you are talking about the equivalent loading or the uniform loading. So we are just solve for the case small portion PQ and just integrate over the what this whole cantilever beam. Okay, so this uniform loading we are talking here on the particular portion, and that what that P is held at a distance x, so L minus x be the bending portion, so W is the uniform load, so W into L minus x, that produces a bending moment about this particular section, and therefore there is no weight being suspended from the free end because this is a uniform loading, remember that. Okay, so the uniform loading which is acting on the whole weight, so that weight multiplied by the length L minus x, which is acting over the average length from the section PQ we consider, and this bending moment is due to the this particular bend W minus Lx acting over the length average length Lx L minus x by 2. So because of the you say the that's the center of gravity, so we consider that this portion is uniform loaded. Okay, and so center of gravity is located in somewhere middle, so we need to take that distance to be average. So this average, hope you understand why we take average over here. Okay, so therefore WL minus x is actually bending moment acting over the length L minus x divided by 2. That's what your expression for the new bending moment becomes. This bending moment becomes W by 2 small w. Remember here small w, and this small w because of the uniform loading on the what the cantilever. So this is the case we are discussing right now. So for equilibrium of this beam, therefore we need to write this W by 2 L minus x whole square, and which is equivalent to again the similar things that we solved in case 1. Yesterday we also talk about y Ig by r, that expression comes of the bending moment, and which gives me d theta by dx, and we find that d theta in terms of a dx because we need to find deflection produced uh, along the what the perpendicular length. So how we write that? Again substituting that d theta over here as L minus x into d theta. That's a similar consideration, similar relations we write in a case 1, and here also we are writing the same thing but with a different bending moment. Okay, so again I say small deflection is a dy that produce, and if you want to find the total deflection produced because of the uniform loading, you want to integrate, okay, this particular expression within the limits 0 to capital L. So WL that we are talking about, so what is the W we define? If we say definition, it is the weight, what we say, it's a weight per unit length. So if we multiply the W with the capital L, it gives me a total weight capital W. Okay, so W is a weight per unit length that multiplied by the capital L, that's the total length of the beam, which gives me a capital W over here is a total load on the beam. Okay, that is what we approximate. So look at here, all the things are considering certain approximation, and then we can write, okay, this expression, okay, general expression for the what, the bending produce, or what we say depression produce, or the deflection we have. Okay, so hope you understand these questions. Hope you understand this particular expression. So I think I can stop here and take your questions. Okay. So these are the three expressions we discussed today. One that we called as, again I took a revision so you will understand what we discussed today. So cantilever, in the cantilever we define a cantilever is a beam which is a fixed horizontally at one end and is loaded at the other end. Okay, that's what we have a cantilever. So cantilever, when it is loaded at the other end, does its own weight be effective or not? So if we consider, we are not considering its own weight, okay, that's cantilever, its own weight we are not taken into consideration, then we we have calculated its value of bending moment, okay, and that bending moment, from that bending moment we calculated the value of how much deflection is produced, okay, of this cantilever perpendicularly, because this is the not originally, and there is a deflection, and that how much is the deflection is produced perpendicular to the length of that beam, okay, that is along the y-axis. So that depression we calculated, small depression we calculated by considering small portion on that particular beam, and further we solved further to get the depression produced by integrating over the total limits of this total length of the beam, and we calculate how this particular free end of the cantilever got depressed, okay, and is depressed by a certain amount that is totally depending upon how much weight you are putting on it, how much length of the beam we have, and it is inversely proportional to the Young's modulus, that is a elastic constant of the material of this particular beam, which may be made up of a what we say plastic or any other material, what we say wooden material, steel material, or any other pure metal or alloy material it has. Okay, typically depending upon the Young's modulus and the geometrical moment of inertia, okay, it depression. So more will be the moment of inertia, less will be its depression, like that. In the another case, we consider its own weight, and that for we again consider some what we say approximation, the midpoint of the center of gravity we consider, the average length of this portion we consider, and that to be added into the earlier W, and we calculated the total bending moment of the beam, and further we calculated how much depression is produced by that particular beam when its own weight is responsible for doing this depression. Okay, in the third case we solved this cantilever, and which is loaded uniformly, and this case we consider by putting all the weights uniformly on this whole length of its cantilever, and consider a small portion, same analogy, same further we solved this third case 3 for finding the bending moment, and then further solved to calculate the depression produce. Okay, so I think 3:45, so I'm just speaking last 45 minutes continuously, so I can take a rest. I can take your questions now. Okay, just wait for a minute, I'll open the settings for you to ask some questions on this particular portion. Just wait. There are certain time needed to open this setting. Okay, just wait.